Welcome, everyone. Thanks, Mike. We are here to announce the winners of the third round for the EPIC Kitchens 2021 challenges. First, before I start, I would like to take a moment to thank all the people who've been on this journey until now, 4 years since we started thinking about collecting the EPIC Kitchens dataset, 3 years since the release of the first version, and 1 year since the release of the extended EPIC-Kitchens-100 dataset, which we are announcing the winners of that round today. If you're around, any people in the team who've collected the dataset, please turn your camera off. Lots of thanks to every individual member. A special welcome to 2 new members that joined this year, Dan and Adriano, who are helping now with running the action recognition and the retrieval challenges. This has been a long journey. We're very proud of all the achievements we've done. And we thank people particularly who have been with us from the first year and who've been submitting for the 3rd year in a row. We're grateful for your efforts because this success could not be possible without your contributions. While I present the background and the dataset of the challenges, if you are here to receive an award or to deliver a talk, and you're currently in the attendees, Mike will be turning you to panelists if you raise your hand. So if you're here to receive an award or to give the talk on one of the winners, it's time now to raise your hand so you can enable your camera. I'll get into the details of how to enable your camera swiftly. But let me first go back to 3 years ago when we released the first version of EPIC Kitchens. And then the notion of the dataset is to collect audio-visual recordings in people's native environments. We gave people very limited instructions saying, please record everything you've done in your kitchen for 3 full days. And that gave the dataset a very different feel than all the datasets had appeared before. There are lots of natural interactions, errors, things a lot less scripted than before. And importantly, the data is completely untrimmed. The recording would start as soon as you walk into the kitchen and would stop as soon as you come out. Naturally, the dataset is unbalanced, and that introduces both an opportunity and a challenge to people working in all aspects of computer vision, from recognition to anticipation, etc. Again, also importantly, we have introduced this notion of doing narrations and then parsing these narrations into their part of speech, from which we automatically extracted verb and nouns, which we then filtered in a combination of automatic and manual effort to come up with the classes you're currently using. The dataset is released with the original narrations as well as the parsed clusters. And this idea, of course, comes from the background of people who've worked in movies and have used all these rich narrations. We wanted to transfer that into other types of activity-based datasets. The dataset is audiovisual. Lots of success has been done in actually using the audio aspect of the dataset. And importantly, the audio in the dataset is both relevant and irrelevant to the ongoing action, which again poses opportunities and challenges. Last year, we have really recorded an extended 2-hour seminar where everybody spoke about their individual contribution and detailed all the challenges. This will remain as a webinar to go to, so I'm not going to go into the details of the challenges. If you're interested in how we collected the dataset and the individual challenges, the benchmarks, I'll refer you to the webinar we recorded and is available on YouTube. Only one thing for people who might have visited us last CVPR and coming back to see the changes. In the previous version of EPIC Kitchens, EPIC Kitchens 55, which is no longer running as a challenge, we had these 2 test sets. We call them S1 and S2 in seen and unseen kitchens. And the idea was we wanted to actually test the performance on these unseen kitchens. There were a bit of confusion. People didn't know how to deal with this unseen kitchens. So in the new version, we've done 2 changes. We first introduced a clear validation split. So there is a train and val split you can train on. And importantly, we kept the notion of S2 by having on every benchmark the evaluation on these unseen participants, in addition to tail classes, but you no longer have 2 test splits. It's a single test split for all the challenges. Updates on the dataset download. We're very happy to know that the data is being used in many, many places in the world. We introduced a few new countries this year, like Argentina and Myanmar. So yeah, please keep using the data set. It is available free for research purposes. And you can download it either via the data.bris or via torrents. And I always keep forgetting, but this year I remember to thank Daniel Stier, who's in charge of everything to do with the downloads, the servers and the torrents. And he's been doing a huge effort to make sure this is available for you to download given the size of the data set. Over the past year, people have visited our website to check the data set and to know more about it again from all over the world. And we have the 2 annotations on GitHub, the old annotations and the new annotations with clear details. Special thanks to many people who made these GitHubs very, very easy to use. Particularly, I'd like to thank Will and Antonina, who've really spent a lot of time to make sure this is as easy to use as possible. Previously, we have 2 runs on the EPIC Kitchens 55. In 2019, we now think of it as we were very lucky that we managed to meet in person and take this picture on the first round of the EPIC Kitchens challenges. And you can look at the technical report for details of the first round of winners. And I'd particularly like to thank those people who are again with us on year 3 and were in this photo. So very much we appreciate your support for the data set, and we hope it's proved useful for your research. Last year, we had a virtual event. And again, we had this group photo for the virtual event, which we plan to do today as well. We have a lot more challenges, as you know. So please hang around, not only when you receive your award, but towards the end. So we have a group photo of all the winners, and you can visit the technical report for details. So this year, we had 5 challenges we announced with EPIC Kitchens 55 on recognition, anticipation, detection, unsupervised domain adaptation for action recognition, and multi-instance retrieval. And I'll start now by announcing the winners. When I announce the winner for every slide, please turn on your camera. If you have your certificate on a mobile, you can show it as per the email instructions if you would like. But importantly, just hang on for a little while and people will take a screenshot that we can keep for you and for us. So we start. Oh, sorry. I wanted to mention that that there were 1 submissions per day and a maximum of 50 submissions. And these were the stats on the challenges. In the first column, you have the number of teams registering. The second column, the number of teams that actually participated in the challenge actively. So they submitted multiple submissions. And on the right side, the number of submissions per challenge. I wanted to note that the action detection benchmark, in fact, while people can submit to the benchmark, they also can evaluate offline. So that's maybe why there is as many submissions to that benchmark. But these are the 10 that appear on the leaderboard that have been submitted to the leaderboard. Again, it's a huge amount of effort on individual benchmarks. And I wanted to thank per benchmark the people who had set it up and the people who reviewed the reports and sent you feedback if you submitted the report to accept them for the general technical report this year. Okay. If you are in the audience, feel free to use your reactions to clap and acknowledge people who are winning. And we'll start by the action recognition winners. So if you're not yet in action recognition, keep your camera off. If you are in action recognition as your slides are shown, we will start with the first place. So the first place goes to a team from the South China University of Technology, JD Academy, and these are the 4 winners. If you are there, make sure that your camera is on and we'll be able to take a picture. Thank you very much, and we will be hearing from this team later. In the second place, we have a large team. I don't know how many members of this team are around, but we have a large team from NUS, from Wazong University, and from Alibaba Group. Great, if you're here, thank you for being here. Okay, I can see some of the, I'm trying to make my screen bigger so I see. So we have 4 members of the team. Thanks for being here and well done. Amazing achievement and very nice report. We'll again hear from you later. In the third place, And for some of these people for the third year going, thank you again for your commitment. And we hope you've enjoyed. And with new people from Samsung and FBK and University of Barcelona, thanks for being here. And this is the third year winning. Big smiles for the camera. We'll take a picture. Great effort on the action recognition. This is our most submitted to benchmark. If you have been submitting, you could have seen that in the last few days, the numbers kept going up and down. Huge competition on the top 3 places. So well done and thank you for your participation. Moving to the action detection winners. A new challenge this year. And in first place, oh, I have the wrong title. I'm sorry. On the action anticipation winners, in the first place, we have the team from FAIR, Rohit and Kristen. If you're around, thank you very much, and we're glad to have you here. Again, a very interesting solution. Please stay around to hear from Rohit about it later. Well done, and thank you very much. In the second place, we have a team from Panasonic. First time submitters to our anticipation challenge, great solution. So if you're around, feel free to turn your camera on. Any members from the Panasonic team? Maybe not, but we hope to hear from them later. Should I wait? I can't see any cameras on. Okay. And in the third place on the anticipation challenge, we have a team from Imperial and SJTU. Yeah, very nice to see you. Thank you very much. Again, new submitters to our challenge. Congratulations and an amazing solution and attempt to do the anticipation challenge. It's a very, very hard challenge with plenty of potential for the future. Apologies for my reordered things. So now we go into the action detection winners. And in the first place, second ranked on the recognition, first rank on the detection, we again welcome and thank the team from HUST, NUS, THU, and Alibaba. And we thank you again for a very well-written report, and we'll hear from you later. I'm hoping Mike and Antonino are catching up with the screenshots. I'm kind of relying on that. And in the second place, we have a team from University of West Madison and Nanyang. Do you have anybody from the second place on the action detection to receive the awards? I believe we're hearing from this team later. If my memory is right, it's going crazy, but I can't see anyone now on the cameras. We move into the UDA, the Unsupervised Domain Adaptation Challenge for Action Recognition. We're very grateful for the number of submissions on this challenge, very new, very different. And the number of submissions shows that there is a need for a domain adaptation challenge in video. Lots of submissions, great 3 winners, and the top prize go to the team from A-Star Singapore. Thank you very much. Oh, a female-only team. I can only be happy. Thank you very much for the submission, and we will be hearing from this team later. In the second prize, we have a team from the University of Tokyo. If you're around, feel free to turn your camera on. Thank you very much for your contribution. Well done. And we will be hearing from the UDA second place later. And in the third place, we'll be hearing from the team from the University of Torino later. Very interesting solution, and we will be asking them to also present their solution later. Congratulations and very well done. Last but not least, we have a single submission to the multi-instance retrieval, a single submission that won over the baseline. I like the fact that we acknowledge our baseline might have been too strong, but for the multi-instance retrieval winners, the place goes to the team from Institute of Information Engineering, Chinese Academy of Science. If you're around, it's now the time to turn your camera on. I acknowledge it might be too late for some people. Oh, yeah, it's coming on. We can see your hand. Hopefully we can see your camera. Ooh. Ah, great. We'll wait, don't worry, no rush. Thank you very much for attempting this challenge, and we'll hope more people will attempt it also next year, and you can come back and still win over a lot more submissions. Congratulations. With that, it's time for a group photo. If you're still with us, keep your camera on. Let's all try to do a group photo. I will stop my share. Also, the team from Epic Kitchens, if you're around, take your time, take your camera, turn your camera on. And we'll try to take a few pictures. Last year, I managed to kind of mix and match a few of these to keep as many people with big smiles as possible. So this. So hopefully we can try that again this year. Many, many thanks. We're really grateful for all your efforts because, you know, we do the work in the background. We've extended the data set. And I don't think we were sure that all these challenges will be of interest to the community. So we're very, very grateful for your contributions. I'm sure between me, Mike, and Antonina, we've taken enough screenshots.
We are taking a lot of pictures. Yeah.
Thank you very, very much for your contributions. Special thanks to the team of EPIC and to all the winners and to the people who've submitted that might not have achieved top 3. We're again very grateful for your contributions, and we hope you'll stay with us now. We move into hearing from the winners. And I'll show you the schedule for your interest. So we chose to shuffle the order a little bit. So we'll hear from the recognition and anticipation later, being our older, maybe more established challenges. We will start with the UDA challenge. And Johnny and Toby, who read the report, said we have to invite all 3 winners to present their all exciting talks. So we'll start by the top ranked team from A-Star, Singapore. And I can invite you now to give your 5 minutes talk. As you can see, we'll stop by the end of the 3 and we can have time for questions. So we're over to Yi Cheng. You're very welcome to share your screen.
Okay. Oh, sorry, I think I'm not able to share my screen.
Okay, let me see the, I think I have done that now.
Oh, okay, now. So can you see my screen?
We certainly can.
Then I will start my presentation. Hello, everyone. This is Yi Cheng from A-Star Singapore. Today, I'm here to present our hand-centric approach for unsupervised domain adaptation challenge for action recognition. This is a joint work from me, Dr. Fang, and Dr. Sun. Here is the outline of my presentation today. The goal of this track is to learn an action recognition model on a labeled source domain and adapt it to an unlabeled target domain. There are many tool challenges in the EPIC-Kitchens-100 dataset. The first one is the presence of distracting objects. As shown in Figure A, for the action wash forks and wash plate, we can see that the action class are highly dependent on the active objects. The second challenges are visually similar actions. For example, in Figure B, the crack egg and open egg are quite visually similar, so it's quite hard for us to distinguish these 2 actions using only the appearance information. Our motivations are as follows. Active objects are generally located around the hand regions. Capturing the subtle difference among hand motions are essential to accurately recognize the target actions. Based on the motivation, we propose to use the hand-centric features, which help to reduce the distraction from background, as well as facilitate domain-invariant feature learning. Here is the methodology. Building upon the TA3N, we propose to learn hand-centric features by leveraging the hand bounding box information for unsupervised domain adaptation on fine-grained action recognition. The overall framework includes two parts. The first one is hand-centric feature generation, and the second one is video domain adaptation. In the first section, we first apply a domain adaptive hand detector to generate the hand bounding box. Then we use the pre-trained models to extract the RGB and flow features. By fusing the extracted features with the hand regions, we can generate the hand-centric features. The concatenation of RGB and flow hand-centric features are served as input to the video domain adaptation module. In this module, we modify the TA3M to design a two-branch classification network, where one branch is for the verb and the other one is for the noun. To achieve high-quality hand localization, we apply an uncertainty-aware domain adaptation network, MEAA, to train a domain adaptive hand detector with very limited hand bounding boxes annotations in the source domain. Here is the framework of the hand detection model. In the training stage, the model takes a pair of images as input, where one image is from the source domain with hand annotation, and the other one is from the target domain without annotation. Here are the experimental results. We experimented with different backbones for feature extraction and different feature types, like including the raw features and hand-centric features, as well as different parameters in the TA3M model. We experimented on the validation set to select the best parameters. Then we trained the model with the selected parameters on the test set. The model performance are further increased with the model ensemble, where we combine the results with multiple models trained on different splits of the testing dataset. In summary, we propose to learn hand-centric features by leveraging the hand bounding box information for UDA on fine-grained action recognition. To obtain high-quality hand localization, we apply MEAA to train a domain-adaptive hand detector with very limited hand bounding box annotations in the source domain. With further performance improvement from the model ensemble, our final submission ranks first on the leaderboard in terms of the top one action recognition accuracy. So that's all for my presentation. Thank you for your listening.
Thanks for sticking to the time. We'll take questions on the three speakers of the UDA challenge. So we'll move directly to the University of Tokyo.
Okay, thank you.
So we have Li-Jin Yang from the University of Tokyo to present. Yeah, perfect. I think you're muted.
Oh, okay, can you hear me?
Yes, we can.
This is Team M3EM from the UDA Challenge, and I am Li-Jin Yang from the University of Tokyo. And our team members are Yifei Huang, Yusuke Scano, and Yoichi Sato. And first, about the domain, unsupervised domain adaptation for action recognition. The goal is adapting a model trained on source domain to target domain by minimizing the domain gap, so which require us to increase the transferability of features. And in order to better deal with this task, we want to leverage multimodal inputs of videos. However, from the GradCam visualization, we can find if we only use the RGB modality, they will focus on objects frequently appear in the source domain kitchens. such as the oil bottles. And if we only use the flow modality, they will focus on regions which have similar patterns across domains. So neither using RGB modality, flow modality, nor similar averaging RGB and flow modalities can get the correct decision. So we argue that it is necessary to enhance modalities by enabling mutual information exchange between them. Thus, we propose a multimodal mutual enhancement module, which consists of two submodules. And the first submodule enables information exchange across modalities and refine features using strings of other modalities. And the second one highlights the regions that are transferable consistently in all modalities. In detail, the first submodule, namely semantic mutual refinement submodule, refine features from two perspectives. Take modality M as an example. The first part is self-refine. Modality M will evaluate the semantic transferability of its channels using its own knowledge, and also a cross-refinement. That means other modalities will use their own knowledge to evaluate the channel of M and give suggestion to M. So giving features of M as an input, we will first use global average pooling and then use the gating operation to get the self-evaluation. And similarly, we can use features from other modalities to get the re-evaluation of channels. And then we can get the self-refined features and cross-refined features. Then we can concat them to get the final refined feature for modality M. Similarly, the feature of M can also be used to refine other modalities. However, after the first SMR submodule, sometimes regions that are similar across domains but irrelevant from the actions may be emphasized. So we use a cross-modality consensus submodule to highlight regions that both modalities think are important. First, giving the RGB features and flow features, we will compute the correlation from different scales to deal with the variety size of transferable regions, and then we will sum them as the final spatial weights. To be noted, our CMC contains various number of parameters, so that will encourage SMR to learn a better representation. And here we show our experimental results. We use the TBM as the feature extraction backbone and use RGB flow and audio as the input modalities. And we can find after combined with our proposed module, we can improve the UDA performance compared with TS3M baseline. Here we also show some Gradcon realization results of activation map before and after refinement with other modalities. I think these examples clearly show that when refined by other modalities, the focus can be shifted to the correct regions. And in order to improve the performance, we further apply model ensemble techniques to ensemble models with the object features as additional modalities and also use the pre-trained hand bounding box. And that's all. Thank you.
Thank you very much. If you have any questions on the first or the second speaker, please put them in the Q&A. We'll take them at the end of the session, and we move into the presentation by the Polytechnic of Torino.
Hi.
Hi.
Can you hear me?
We can.
Okay, I share my screen and me and Mirko split our presentation. So I will start and then I leave the work to Mirko. Okay, can you see my screen?
Yeah.
Okay. Hello to everybody. I'm Chiara Frizzari from Politecnico di Torino, and today me and Mirko Planamente will present our submission to the EPIC-Kitchen Unsupervised Domain Adaptation Challenge. First of all, let's give a brief overview of the approaches that we used. We noticed that the EPIC-Kitchen Challenge dataset is composed of different domains. So we thought that it could be beneficial to use a domain generalization approach to deal with the domain shift under this setting. The domain generalization approach consists in not seeing the target data during training, and it aims to extract a shared knowledge across the different source domain to obtain a domain agnostic model that can be adaptable to any unseen target one. This approach, of course, is easily extendable to a domain adaptation setting by training also on unable target data that were available from the official training split of the challenge. Moreover, we also use the unsupervised domain adaptation techniques between different models to improve consistency between the different predictions from the different models. I present now the domain generalization approach that we used. It is based on an existing approach called relative normal alignment network. This takes an input, different modalities, different input modalities from different source domains, and it aims to introduce a cross-modal loss on the features extracted from both audio and visual input. In particular, it performs a multimodal domain alignment between the different audio and visual features by rebalancing the contribution of the two during training. This is done by ensuring that the mean feature norm of the audio modality is the same as the mean feature norm of the RGB1. This loss is minimized together with a standard cross-entropy classification loss. This method can be easily extended to an unsupervised domain adaptation setting by rebalancing the contribution of the two modalities, not only on source domain, but also on target one. So finally, we will have the contribution of the relative normal alignment loss on source and of the relative normal alignment loss on target.
Our final architecture is composed by different well-known feature extractors, and the scores are summed together with the RNNet prediction for both verb and noun. The first UDA technique applies to the other backbone is the temporal attentive adversarial adaptation network. It consists on an adversarial approach through the gradient reversal layer, and domain adaptation technique to guide the temporal alignment and the minimization of attentive entropy. Starting from the concept of rebalance proposed by RNNet, we extend it in order to rebalance the contribution of other backbones in order to avoid that one backbone dominates the other. In this slide, we just display the verb prediction for simplicity. And so we integrate in the temporal relation module the concept of norm rebalance and among the source and target data, and among from the different backbones. And the loss introduced is called temporal normal alignment. We also introduce a second loss called minimum entropy consensus. The goal of this loss is to force the different backbone to converge on the same prediction. We can see an overview about our final architecture used for the competition. We see very rapidly the results obtained by our approach. First of all, we compare our net in domain generalization setting with respect to the T3N. We can see without the use of target data, our method overcome the result to the other domain adaptation approach. And also we prove the complementarity about the two. Then we also validate the two loss proposed. Both of them guarantee an improvement on a three category on the validation set proposed by the authors of the challenge. And then finally, this is the result obtained by our submission. We achieve a third position. In particular, our best results are in the verb top 1 and all top 5 accuracy. We believe that the improvement to the verb category is because its category benefits more by the domain generalization setting used in the first step. Thank you for your attention.
Thank you.
I can't hear you.
Yeah, we can't hear you.
That's wise. Thank you for telling me. I was saying, let's have the three presenters who'd like to share to switch your cameras on for any questions. And while we get questions, I'll ask each of the presenters to say a piece of advice based on the experience you've had with this challenge. If someone wants to contribute to this challenge or submit to this challenge next year, what would you think? What was the most important advice you would give them based on your experience? And let's start with the team from A-Star Singapore. What would be the piece of advice you would give to people who would want to participate in the challenge next year? Yeah, you're muted again. We're all playing the same trick.
Sorry, I think based on our experience, maybe we can explore more on the characteristics of the data sets to make improvement for the task. Yeah.
Yeah, so understand more the characteristics of the data set. And the University of Tokyo?
Yes, I agree. I think maybe we should use more egocentric cues for the application data sets.
Yeah. Torino.
I think to focus more on the relevant part of the action, like objects, because there is a lot of background, and this is what is dangerous across domain. And in general, the training are long, so don't give up and keep patient.
Yes,
and I don't know if, yeah, I don't know if Mirko wants to add something.
In my opinion, it could be also interesting to analyze also kitchen that you have never seen during training. So a bias shift due to the background and not only the temporal shift.
Yeah, so we focus on this challenge in the shift in recording 2 years later, as opposed to the shift in a new kitchen. But yeah, idea.
It's similar to unseen test split in the first.
Correct. So there's a question on the first submission is, why did you decide you needed a hand detection you needed to do a domain adaptation for the hand detection? Did you feel the hand detector did not generalize to the new environments? Unmute.
Sorry again. Yeah, actually, because we think this track is for domain adaptation, so we think maybe it's better to use the domain adaptive hand detector. And also, we do the experiments with the pre-trained hand detector, and we find the domain adaptive one is can give better results. Yeah.
We have a question from Antonino, if you would like to ask it.
Yes, sure. So I have a question for the third team. So at some point you mentioned that you add a term to let the different models converge to the same prediction. And I wonder if this is enforced even when the prediction is known to be wrong, and if this in some sense reduces the natural effect of ensemble of models which make different predictions, different mistakes, and I mean, overall a better model.
I don't know if Chiara wants to answer, but
in general, since it considers the probability for the prediction, it tends to maximize the agreement for those classes whose probability is max. So in general, it should minimize those cases where the probability to predict wrong classes is less. So I think our loss should take into consideration also this aspect.
Yeah, and also I think that the temporal hard normal alignment give the opportunity to rebalance the contribution of each backbone in order to have a good comparable prediction for the three backbones, in order that the backbone that are more useful for each class, we believe that is the prediction that guide the other two predictions.
Yeah, for example, if there is a backbone that outputs a very high prediction for a wrong class, by rebalancing the contribution of all the backbones, we ensure that the prediction importance is equal for all the backbone, and does not prevail the one that has only like a higher probability, but we keep them equal.
Okay, I see. Thank you.
And for the team from Tokyo, you mentioned egocentric cues. There's a question about, do you have any particular cues in mind that you think people should attend to? Is it the camera motion? Is it the hand?
I think maybe other than hands, maybe we can also use some gaze prediction models trained on other egocentric data sets to use on navigation data sets and to use gaze and as an additional information.
Great. Thanks a lot for all the submitters and for the winners and for the time to come, regardless of your time zone, to present. We very much appreciate your efforts. And you'll always say we were the first winners of the UDA challenge of EPIC Kitchen. So I hope this proves useful for you in the future, and we will see submissions from you next year. Thank you very much. We'll move to the next session where we are having the action detection and recognition. So this is the team from, the presenter will be Zhuang Huang. It's a team from NUS and the University of, and I'm very bad in names now, I've read so many names. So they were the top winners on detection and the second winners on recognition, and they'll give us a combined talk on their solutions. We can see.
Hello. Okay, thank you. So hello everyone. This is Huang Ziyuan from the National University of Singapore, and I am here on behalf of the team to present our solution to the action recognition and action detection task for the EPIC Kitchens challenge. Recently, the computer vision community has witnessed the rapid development of the transformer-based architecture because of its great potential for a strong performance. However, compared to the ones used for images, video vision transformers are less explored in terms of the different training strategies. Therefore, today we present empirical results for training a stronger video vision transformer used for both action recognition and action detection. So for video vision transformers, we follow most of the settings in the factorized encoder structure in the VIVIT paper with a tubelet size of 16:2. After the input video is tokenized, spatial encoder is applied on each of the frame embeddings before the class tokens for all of the frames are gathered and processed by a temporal transformer. The class token of the final temporal transformer is connected to two classifiers, which generates the verb and noun predictions. For action recognition, our explorations include different initializations, augmentations, data sources, as well as the action prediction strategy after the noun and verb predictions are obtained. And first, we pre-train the model on large public data sets in preparation for further initializations. Next, we fine-tune the pre-trained model on the EPIC-Kitchens dataset. Compared to the ImageNet pre-training, pre-training on video datasets clearly has an advantage since the temporal transformer is also trained in this way. It is also natural that when the models are pre-trained on larger datasets, the performance will be improved. And because the egocentric videos in EPIC-Kitchens dataset have a domain gap to the ones in kinetics, we tried to initialize from something v2 pre-training. It can be observed that although something v2 only has over 220K videos, which is much smaller than the over 600K videos in Kinetics 700, there isn't a large performance gap between the two initializations. This shows that pre-training on egocentric videos is more reasonable for egocentric action recognition like EPIC-Kitchens than pre-training on datasets like Kinetics. However, the fact that Kinetics 700 initialization has a better performance also shows that the scale of the dataset can offset the domain gap and generate a generalized representation. Further, we used models pre-trained with higher resolution as our initialization, which achieved less accuracy than the one pre-trained with smaller resolutions. We also found that better input quality, stronger augmentations, as well as larger input resolutions are beneficial to the classification. For the input resolution, raising it from 224 to 320 achieves an improvement of 2.4%, while 384 is only better than 320 by 0.6%, which means the performance gradually saturates with the increase of the input resolutions. In addition, a usual approach for calculating the action score is to first calculate a video level verb noun prediction for each video by aggregating predictions over different views before calculating the video level action predictions. We found that if we altered the sequence by first calculating action predictions for each view before aggregating the action scores for different views, a notable improvement in the performance can be observed. This improvement is cheap as this process can be simply altered in the evaluation process without the need to retrain the model. When compared to the original paper, an improvement of 3% is observed by using our training recipe. Altering the temporal stride to match the FPS sampled in the pre-trained model can further improve the model performance. When using optical flow, the performance on verb prediction is less affected, while accuracy on noun prediction drops by around 16%. Using our training recipe, we achieved a 5% improvement on the timesformer model as well, compared to the one used in the original paper. Our training recipe is further applied to convolutional models where it is also shown to be effective. And finally, we ensemble the models and achieve an accuracy of 51.7 for action prediction on the validation set and 48.5% on the test set. And for the temporal action localization or the action detection, here is an overall framework of our solution. The whole framework can be divided into 3 sections. In the feature extraction stage, we divide each video into clips and we exploit the model trained for the action recognition challenge and extract the verb prediction, noun prediction, as well as the features for each clip in the untrimmed video. We show in our experiments that without the verb classification and noun classification results in this stage, and directly use the extracted feature to generate the proposal as well as the classification results in the next stage will result in suboptimal performance. And the second stage generates the proposal using the extracted feature. We use sliding windows because the ratio between the duration of the untrimmed video and the action is large. The sliding windows are uniformly distributed along the temporal dimension, and clip level features covered by each sliding window are fed to the boundary matching network to generate the proposals. In the final stage, detection results are generated according to the verb classification, noun classification, as well as the proposals. The classification results for each proposal are sampled from the clip level classifications with 10 views sampled for each proposal. Finally, the verb and noun predictions are fused with the proposals to generate the detection result with action predictions. For the first 2 experiments, we discard the verb and noun predictions from the pre-trained backbone and use the features extracted for each proposal by the boundary matching network for classification. In this case, we observe difficulties in conversion to a generalizable detection model. In contrast, when we exploit the prediction results from the pre-trained model, a notable improvement over the baseline could be observed. Therefore, this can serve as a stronger baseline for the egocentric action detection task. Overall, we achieved the first place in action detection challenge and the second place in action recognition challenge, and codes will be released soon together with our recent proposed MOSI. Thank you.
Fantastic. Thank you very much. And we'll take questions after the second talk by Qinlin Zhang.
Yeah, sure. Thank you.
Thank you very much. Yeah, we can see your slides. We can't hear yours yet. Let me ask you to unmute.
Yeah, hello everyone. So I think you can hear it. Yeah. Hello everyone, I'm Chenlin Zhang from Nanjing University. Today I want to introduce our submission to EPIC-Kitchens-100 Action Detection Challenge. Our team includes myself, Jin Xingwu from Nanjing University, and Ying Li from University of Wisconsin-Madison. This work was done when I was visiting the University of Wisconsin-Madison. So temporal action localization is to identify onsets or offsets of an action instances and at the same time recognize their categories. Yes, so several recent work have developed deep models for temporal action localization. Okay, so Several recent works have developed deep models for temporal action localization, but none of them are specially designed for first-person videos. Yes, so let's consider this same first-person video again. We will look at a few keyframes from clips within different parts of the video. Out of these 3 clips, which one or ones is part of the action of cutting leeks? The middle one seems clear cut, yet the ones on the left and right are not super clear. So here is the answer. The first clip is before the action starts, while the second one is around the action center, and the last one is close to the end. Thus, the first one is out, while the rest 2 belongs to the action. Our observation is that clips near the center of an action are less ambiguous, while clips near the action boundaries are more challenging. In fact, this is widely known in the action localization literature, and especially for the first-person videos. So if the center clips are easy to recognize, what if we only recognize these center clips? This is not a brand new idea, and now we will go next. To this end, we propose a new action representation, which presents an action into classified moments near the center and regressing distances to the action onset and offset. With the action representation, we end up with a single-stage anchor-free model for temporal action localization. The proposed model is flexible because it doesn't need manually designed anchors. And the proposed model is also efficient because it is a single-stage method and does not need action proposals. Yes. Now we introduce our model architecture. Our model consists of 3 key components. The first component is the center-based representation. We represent action as center moments plus starting and ending distances. The second is a multi-scale transformer encoder that converts video into multi-scale features. And the third is the feature pyramid, designed to capture temporal dependencies at different scales. More details will be included in our archive paper soon to be released. Yeah, so, okay, so now let's look at our results. We first present our results on EPIC-Kitchens-100 validation set. In this experiment, our models use slow-fast RGB features. The results are in the right feature. We list the baseline methods, include BMA and GTAD for comparison. Our results are in green. Yeah, compared to, okay, so that's this side. Yeah, our results are in green. Compared to published baselines, our model have a significant performance boost over all 3 subtasks. Our model achieves 13.7, 12.3, and 7.2 MAP on verb, noun, and action subtask. Next, we show our results on EPIC-Kitchens-100 challenge. The results are in the right feature. In this feature, BMA and our method both use slow-fast RGB features. The top-ranked method from Qing et al. Uses stronger backbones just as they said VIVIT models. Thus, our method performs better than BMA, but have a major gap with Qing et al. And our next step will be using stronger video features and incorporating object detection outputs. And to conclude, we propose a new action representation. We propose to represent action as center moments plus offset. We explore using transformer for action localization, not just for action recognition. And our model achieves strong empirical results on major benchmarks. The paper and the code will be released. Thank you, and I welcome all the questions. Okay, I think, yeah, this is my presentation.
Thank you very much. Let's have we can stop your share screen and then have the 2 speakers, if you'd like to turn your microphones or cameras on. And we'll start by the same question we asked the last session. What is your advice to the people who might be wanting to attempt the action detection or the action recognition challenge next year? And let's start with the first speaker.
Yeah, one of the greatest suggestions is probably to use our released codes and models, which will be released soon, because we have trained some strong baselines. And if you start with our codes and models, it will be easier to get started. And second, maybe explore more training techniques for the existing models, because this data set is, although it has been proposed for several years already, but the EPIC-Kitchens-100 is only being proposed for less than a year, right?
Yeah, just less than a year. It's 1st of July when we released it, yeah, last year.
Yeah, so yeah, maybe more explorations on the training recipes for existing models will be of better benefit than proposing some new networks to solve the task.
So you think better training on the current benchmarks. Anything else that you think people should start from?
Also start from examining all the data given by the data set, because we only used RGB modality. I think the hand positions or maybe the interactions with the objects are also provided, but we didn't use that. I think that will provide a stronger signal for the interactions, which we currently lack in our approach.
Thank you. And Nanjing University, yeah, the second.
Yeah, I think it is essential to have stronger action recognition backbone for this action detection challenge or action recognition challenge. I agree with Ziyuan Huang's idea that according to his experiment, and it is good to use the stronger backbone. And besides the strong backbone, I think also a major part is that we can apply object detection feature as I just illustrated in our slide, that using object detection, something like hand object detection will be. Yes.
Sorry, there was yeah, go ahead.
Yeah, so I think there are two major steps for this challenge. Yeah, so I think for this action detection challenge, since we are not doing well as we are as other action recognition methods on ActivityNet, I think a major issue is the action recognition performance. Yeah.
Great. There is, before I ask the next set of questions, there is a question on the Q&A about the experience and suggestions for evaluating the action segmentation task on EPIC-Kitchens. And it was directed to the University of Tokyo that had attempted that. The response from Tokyo was, we have a huge overlap in the actions between EPIC and EPIC-Kitchens. So one frame might belong to multiple actions, making it not really a standard approach to the current action segmentation approaches that assume that you have one label per segment. But any of the speakers would like to comment on whether they had considered or whether they think these approaches can be used for multi-label action segmentation? Not necessarily. So that, yeah, so the action segmentation tasks really take an offline video. Maybe Antonina wants to comment on that, because our experience with the detection and the segmentation benchmarks, they all expect the videos to be of comparable length. And then part of our main issues was that, you know, our videos are very, very variable in length. Do you want Antonina to say more on that?
Is this related on the issue of segmentation or?
Well, both, huh? Because these take an offline video and make an evaluation of all of it. I'm assuming segmentation does work offline on the full video.
Yeah, so I just want to add something about the segmentation thing. At least our main motivation behind proposing this as a detection task, because I understand that this kind of guides the way people look at the data set, because we define the challenge as detection rather than segmentation. The main reason was the huge overlap. So it was not clear how to use segmentation methods out of the box. Maybe there's some clever way to do so, maybe with multi-label approaches. I know that there's something that does multi-label, but it just didn't look like the most straightforward thing to do. And I agree with Dima that hearing from people who engaged in the challenge, even hearing about their thoughts is probably, I mean, best. I don't know if they tried segmentation approaches, but that was our main motivation.
Yes, for people's interest listening, 70% of our frames are labeled with an action. So background is around 30%. And if I remember correctly, like around 60% of our actions have some element of overlap. And the stats are in the rescaling egocentric vision work. I'm just scrolling if there are any more questions. There is an open question. Sorry. Besides the huge overlap, did you also sense other infeasibilities of performing segmentation on Epic Kitchens? I think it's the variable length of the videos. Some of our videos are 5 minutes, 7 minutes, and some could be 40 minutes, 1 hour. So currently these benchmarks take, 60% of the frames are of the actions have overlap in them, not of the frames. I don't know if we have a number of the frames exactly that have multiple labels. But you can, yeah, it's 6% of the actions labeled. What was I saying? Yes, so most of the action segmentation take the full video and analyze it. And that makes it very, very difficult if you have short and long videos to have the same approach that operates on variable length. Currently, all previous works assume that all the videos are of comparable length. Comparable means they could differ, but they're not like 5 minutes versus 1.5 hours. So on that level, it was very difficult even to decide the rate at which you would extract features, etc., because none of the approaches deal with this variability. The videos are recorded in a way that you would start recording as soon as you walk into the kitchen and stop recording as soon as you go out. Sometimes you're just in to drink some water and make a coffee, and sometimes you're there to prepare a long meal, particularly the meals in Italy just take very long to prepare. So you'll see some of the long videos from different parts of the world. So I hope this answered the questions. I had a question on for the first speaker on the insight on attempting to train on something V2, because this is something we thought about given that it has hands and it has a good variability. So what's your insight on why it proved less useful as a pre-training? Is it because of the size of the data set, the quality of the recording? What was your feel?
Well, my feeling that it is mainly because of the size of the data set, because something V2 only has around 220K videos, while Kinetics 700 has around 600K videos. So, but the performance is actually comparable because there's only around 0.5, 0.6 gap between the models pre-trained with something and the Kinetics. Yeah. So the main thing that I feel is
neither of these are perfect for pre-training, and worth noting, if you're around until the end of today, you'll be able to hear about this new dataset, Ego4D MSF dataset, which we, Giovanni, and other 12 universities have contributed to collecting, University of Tokyo. So many of the people present here have been part of this huge effort to be released towards the end of the year. Hopefully, this will give us the dataset for pre-training that we all need. And of course, new challenges of relevance and different from what Epic Kitchens offers. With that, let's thank the two speakers for today, for this session. Sorry, I'm already getting tired. The two speakers for this session, and we move into the action recognition talk. So the first ranked submission on action recognition from CSUT. We are ready for your slides. Great, we can see your slides. We can't yet hear you.
Hello?
Now
can
we
you hear
can.
Me?
Yes, we can.
Oh, yeah. Hello everyone, my name is Zheyu Jiang. I'm from South China University of Technology. It's my great honor to be here to introduce my method. During the challenge, we define a simple fusing architecture to fuse the features extract from different backbones, different video clips, and different prediction tasks. We train our backbone for 4 prediction tasks: predict first, predict now, predict first and now, and predict action. Action variable is the combination of first and now variables. So fast imports multi-key averaging during the test task. Before our method, we train 4 types of so fast with different feature models, different number of the input fed, and different training and validation speed. Firstly, this so far is trained for 4 times for different prediction tasks. All in all, we have trained 16 models. And then for each model, we extract 10 video features. The strength of the feature is the number of keys multiplied the dimension. And this is the overview of our method. Model A_A can denote that the features extract from model A as a prediction task. We use the features extract from 2 types of the so fast as input. In this figure, we take features extract from model A and model B as input. All the features have the share vulnerable cast token followed by the position embedding and the fusion block. During training, each fusion block is followed by a classification layers to predict none, first, and action scores together. At the testing time, we average the score of all the fusion blocks to predict more better results. This is our fusion block. The fusion block is based on the transformer. In this figure, for example, that feature model A extract from model A. Action prediction task as input 1 and take the feature extract from model B as input 2. And this fusion block can fuse those features. All in all, our method is very simple and effective. And let's see the result. We use an ensemble of a set of 6 models as the final result for testing set, which are trained by the combination of extract feature from different so fast as input. Final result can achieve the first place in terms of top one access. That's all of my pronunciation. Thank you so much for your attention.
Thanks for your presentation. And now we move to the top place, first rank on the action anticipation. We'll take questions on the 3 talks at the end.
All right, hopefully everyone can hear me and see the
Now
slides.
we can, yes, go ahead.
All right, hi everyone, I'm Rohit and I'm presenting our work on anticipative video transformer for the EPIC-Kitchens Anticipation Challenge. We propose an attention-based architecture for predictive video modeling. At every frame in the video, the model attends to all the frames it has seen up to and including the current frame to predict future actions as well as future visual features. Building upon transformers, it is capable of modeling long-term temporal dependencies efficiently. And using this sort of causal attention architecture where it's attending to all the frames it has seen so far, it is also able to leverage the natural intermediate supervision present in videos, such as predicting the intermediate visual features, to encourage the model to learn the sequential nature of actions. We further extended by using an attention-based backbone as the visual feature generator, leading to an end-to-end attention-based architecture for video understanding. And as we can see here from the spatial attention maps, the model spontaneously learns to attend to hands and objects, which as prior work has shown is especially important for understanding egocentric actions. Now going over a bit more details, let me start by describing our backbone architecture. So our model is compatible with various different kinds of backbones, and in experiments we use approaches like TSN, which is a popular frame level backbone, as well as CSN, which is a popular 3D convolutional backbone. As well as we also propose our own new transformer-based backbone architecture, which we refer to as AVTB, and it's essentially based on the recently popular VITB architecture. This architecture essentially patches up the images into patches and projects them linearly, and then passes them through a transformer encoder to get a representation for each frame. Now going over the head architecture, our head is essentially implemented using a causal transformer decoder. So this is, again, sort of very popular in language literature, where for things like text generation, people use causal attention to attend to all the words it has generated so far or seen so far to predict what the next word will be. And similarly, we apply it to videos where this transformer decoder essentially attends to all the frame or the features that come from all the frames so far, and use those to predict what the features for the future frame will be. So for example, in this case, for let's say at the frame Z3 or the frames for whose features are Z3, the feature prediction Z3 hat will essentially attend to Z3, Z2, Z1 to make the feature prediction. And similarly, the final prediction, which in this case is the ZT hat, will attend to everything. And this will be this will essentially correspond to the final output of our model, which predicts, given this clip, what the next action will be. And the linear layer on top essentially just decodes the future feature into the actual action classes, which is what's used for the final evaluation. Now, how do we train this model? We use three losses: next action anticipation, feature anticipation, and current action classification, which I'll describe next. So the first loss, next action anticipation, is the most straightforward one, where we essentially supervise the final prediction from our model, which is ZT hat, with the actual future action that is labeled in the dataset, using a simple cross entropy loss. Next, we use we incur this feature anticipation loss, which is essentially, you can think of as sort of an imagination loss, where the intermediate feature predictions, and like the Z1 hat, Z2 hat, and so on, are actually used. We try to match those to the actual future features that we have in the video. So since we're processing the full video, we also have the actual ground truth features for each of those positions, and we can incur a loss between our predicted feature and the actual feature. In our case, we simply use an L2 loss, which we found to work pretty well. And similar losses have been used for unsupervised representation learning as well. And then finally, leveraging sort of the dense labeled aspect of EPIC-Kitchens, as was described in a few talks earlier, we also supervise our intermediate prediction. So since we are sort of predicting all the intermediate features, we also supervise for whatever portions of video that are actually labeled, we would supervise with the actual action that is labeled in between. And wherever nothing is labeled, we just don't incur any loss. Now we train the model with all these three losses combined, and now I'll go over our experiments and analysis. So the first experiment ablation is to see how much do we gain by having all these intermediate losses. And here I'm showing numbers on EPIC-Kitchens-100, and these are averaged over two backbones. So a fixed TSN backbone, which is just TSN features as used in prior work, as well as an end-to-end AVTB or the attention-based end-to-end model to get a more robust estimate of the performance. And as you can see, compared to just using the L-next, which is just predicting next action, leveraging these intermediate losses of predicting intermediate classes and regressing for the intermediate features leads to an improvement over that. And then finally, using both of these losses together gives us the best performance. Now going over our overall performance. So we started by first comparing our RGB only models, and we started by comparing it to the baseline and prior work, our STM. And as we can see, our model, just the head model applied to the exact same features from TSN is already able to perform comparably or slightly better. Next, we also tried replacing these features with features from a model trained on weakly supervised videos, specifically I65M. Interestingly, we found that this by itself was not super helpful on the EPIC-Kitchens-100 task. And we believe it's partly because of the sort of metric used here is recall at 5, as opposed to, let's say, the top 5 accuracies used in prior versions of this data set. And we found that once you're equally weighing all the tail classes, like these pre-trained models were not as effective. Next, we have all the results with our end-to-end attention-based backbone using different kinds of initializations. And here we found that having better initialization gave a clear boost. So having ImageNet21K initialization was quite helpful. And then finally, we also tried training the model for on even longer videos and for longer, more number of epochs. And we found that that was actually also very helpful. And this is another observation we have. Our model is quite good at leveraging long temporal context. And this is an example of what we saw that gave another 1% improvement. Then we also have similar analysis on object modality and flow modality, and we got similar gains. And then finally, we late fuse a bunch of these models for our final submission, which I've shown as the ticked ones here, and that got us an overall action recall of 90.2 on the validation set, and this was our submission, along with the same models, or some of these models also trained on the train plus val set for the test submission. And yes, so our final model was able to get pretty strong performance, as we know. Yeah, with that, I'd like to conclude my presentation. We have presented AVT, which is an attention-based video architecture for sequential video modeling. We've shown these auxiliary losses are quite useful in learning good representations, and we are able to obtain strong results on EPIC-Kitchens' next action anticipation task. And we also found that the model itself is also amenable to more longer-term feature prediction by simply auto-regressively rolling it out, as shown here. And I'm happy to take any questions, I guess, after the other talks.
Thank you very much, Rohit. We'll take questions after the final talk by the second action anticipation work from Panasonic. Hopefully they were not here for the prize, but hopefully they're here for the talk.
Hi.
Hello.
Hello. Sorry, a while ago, I wasn't ready for camera and mic. Yeah.
Great.
Wait a minute, we'll share my slide.
Can I take a picture of you with the mobile phone? I'll then edit it and put it. Where are you?
Can you see your slide?
I can see your slides for sure. Do you want to raise your mobile phone and then I will edit your picture into the prize? Do you want to hold your phone with the?
Oh, okay.
Yeah, perfect. I'll edit it into the other things. Thank you very much. So yes, over to the second place on the anticipation challenge.
Okay, let's start. Hi, my name is Taro Yamamuro. I'd like to thank you for giving me the chance to speak here today. Today, I'd like to introduce our approach to this competition. Title is Submission to EPIC-Kitchens Action Anticipation Challenge 2021. Let's start. In this slide, I describe our base model. We use rolling and rolling LSTMs and modality attention because past work have shown it to be effective. From this slide, we will introduce the points we devised in this competition. We added 3 optimizations to base RSTM. First, level smoothing based on one vector got by pre-trained BART. Second, uncertainty modeling loss to separate action frame and background frame. Last one, approach for imbalance dataset, class balance loss, and defaultivate. All approaches improved performance from the base model. From next slide, I will briefly explain 3 approaches. First, our level smoothing method in past work, level smoothing using word vector is effective for action anticipation task. Mostly, word vector is got from graph. Then, to get a better vector than graph, we try to get a vector using pre-trained BART. I think this approach has 2 strong points. First, get a vector that considers the relationship between verbs and nouns. Second, assign higher value to labels which are similar to correct labels. Next, uncertainty modeling loss. We think that current past action contributes to prediction of future actions. However, annotation of action frame takes a huge amount of time and effort. So we adapted a technique that allows us to separate the action frame and the background frame without annotations. Please refer to the original paper for details of error function. In short, cell learning is performed on the extracted features, and optimization is performed by maximizing the norm of action frame and minimizing the norm of the background frame. This method can also be used in combination with the level smoothing mentioned above. Next, class balance loss and defaultivate. As you all know, the EPIC-Kitchen dataset is very unbalanced, like this image. Therefore, we adapted this method to improve the prediction accuracy of the tail class. Class balance loss defines and weights the effective number, which is actual number of data for each class. Beta is a hyperparameter, so it needs to be tuned for the dataset. Defaultivate is a simple training scheduler that starts waiting after some learning has processed. For example, if we train model 100 epochs in total, it will be well to start waiting after 50 epochs. As a result, this approach was very effective in this competition. One more thing, as a device to improve the score, we adopted test time augmentation. To change the distribution of prediction, we randomly erased up 2 frames of rolling LSTM input frames. Our final score was mixed with TTA score and without TTA score by parameter alpha. Finally, I'd like to introduce the result of the competition. Our best model is combination of RULSTM and class balance loss and defaultivate and test time augmentation. In validation data, this model recorded 18.27% in overall action. In test data, we got 14.82% in overall action. Thank you for listening.
Great, thank you very much. If I can ask all the speakers, to turn on. Let me start by the question we asked all speakers in order. What would you advise someone who would like to participate in the challenge next year? What is your main advice? And we'll start with the first speaker, so that's Ziyu. You're muted. We can hear you, I think. Hello. Maybe we'll come back. Let's move to Rohit. What would be your main advice to new people participating?
Sure. I think, so we found pre-training was very helpful, and at least in our work, we only went so far as Emission 21K. I feel things like kinetics would have also been useful, and potentially with even more advanced architectures like MZIT or BibVit and so on. Temporal context was also very helpful. And I think we have like plateaued that part. Like I think like we could have pushed it further potentially. So that would be something else to look at as well. And also other modalities. So for our method, the object and flow modalities were trained on fixed features, which I think could also put in end-to-end and potentially get better performance.
Thank you. And Yutaro?
Hi.
Would you like to advise people who would like to participate in the challenge next year? What would be your main advice?
Oh, I think this task is very difficult.
That's why we need you.
If you participate in this competition next year, you will research recent work. Sorry, I'm good at English. I'm not good at English.
We understood that very well. Ziyu, would you like to come back and comment on this? Don't know whether your microphone is working. Maybe not. We have a question in the Q&A. I have another question for the paper, cross-domain, first-person, audiovisual, action recognition. Oh, so that's from Torino. Okay, so I guess the Torino people, if you're still around, there is a question in your Q&A for you to answer. I had a question on the for Rohit about you talked about the context being 10 second and 15 second. So in this case, are you changing your sampling, but so you have the same number of inputs, or actually increasing the input? And what is the input, as in how many inputs do you have in the 10 second?
Right. So we use 1 FPS, so it's 1 frame. So 10 seconds is 10 frames, and 15 seconds 15 frames. So we did not change sampling. We did not see a big difference by the sampling. And also, since our model is sort of designed to predict the next feature along the video, and then since the problem setting is set up as you have to predict 1 second in the future, so 1 second seems to fit well with the problem setting.
And I noticed your comment about the IG 65 million, which was useful for training in the first round. I think because the data set is now bigger, I think we haven't had the same advantages on these data sets, because now the EPIC-Kitchens-100. I've heard other people saying the same thing, is that it didn't prove as useful as first time. And I have a question for the second anticipation. So for Yutaro. So you said that there were very hard actions and long tail, and currently some of the long tail is different between verbs and nouns. So we have different distributions between the verb classes and the noun classes. Did you deal with verbs and nouns differently, or you assumed the same long tail in both of them? Did you get my question? Was it hard?
Sorry, one more, please.
I'll try again. So the verb classes distribution, the long tail, is different from the noun class distribution, the long tail. Yeah. Did you deal with them differently or in the same way? They're not exactly the same long tail distribution.
Okay. I deal with same way. Okay.
Dealt with them in the same way. We have a question from Changing Ding, and I think I can allow you to talk. So I would be enabling your microphone.
Okay, can you hear me?
We can hear you now.
Oh, okay. I'm from SCCOT, the first place for the action recognition task. I want to offer my suggestions for the next year's challenge. The first thing that I think is that the kitchen is a crowded situation. I suggest that we may take 3D devices to capture 3D data. So the 3D data may well handle the occlusion problem in the kitchen. All right. The second suggestion is that I think the data is very big. it may be challenging for university teams to participate in this challenge. So I suggest that we may use only short videos and officially sample some fixed number of frames. So all teams use the same small data. So this allows us to pay more attention on the methods. Another suggestion is that we may consider multiple people are in the same situation. Just now, this data assumes that there is only one people in the kitchen, right? But in the real application, I think many people, several people may participate in the kitchen.
Mm-hmm.
So
for both things, I would very much encourage everyone to stay around till the end of the work. You're going to see a new data set with very different social also benchmarks, the Ego4D benchmark. So that's not something we anticipate Epic Kitchens to extend into. Our main idea with Epic Kitchen is that there is one person, so we don't have to do any anonymization or any privacy. People are not talking, etc. But yeah, there are upcoming data sets with similar interest. And thanks to people from Torino for answering the question. With that, I would like to thank very much, we just ran out of time, thank very much all the participants and congratulate all the winners. We have done an embargo, so we haven't announced the winners. I believe Giovanni had just put that on Twitter, so you can feel free to tweet your certificate and we will do an official announcement sometime tomorrow. Hang on, this is the end of the Epic Kitchens challenges, but the Epic workshop continues.